In the real world, the problem, like these two type of measures, they're not perfect in one side or the other side. Are you with me? Even though you from the other feature, you can find the one is the antenna dominant, another is the wind dominant. They might be crossing the line, but from other feature you distinguish them not. See, here's the problem. There's a misposition. Like this guy looks like the circle, the empty circle here, the void circle, bounce to that side. Can you see? Go to the solid side. Can you see? And then the solid point here goes so far in this cycle side. And if now you mix like this, it doesn't matter where you have the line. You cannot separate them. Are you with me? There are something you just cannot separate. Clean. You got to have some error. Yeah, the error did not come because you did a bad job. Because the error is in the data. Could it be the data is wrong? Could it be right? The data is right. It's just like that. You know, even with human being has a kind of outlier, different thing. So in that case, we got to get a soft margin. What means soft margin? Means we are going to get the margin down anyway, but we are going to take some error because it cannot be perfect. Let's give you an extreme example. Let's give you a random class. I got all things wrong in the first place for the antenna wind dominated or the wind dominated. I just messed up all the classes. My data is all wrong. How can you separate them? You can't, right? But if these two data is either wrong or just it is right, but you cannot separate, what you can do? Well, you still say, hey, let me do two things. I still wanted to get a fair good margin to split them. But I'm going to try to minimize the error. Just get this, because in this case, intuitively, I have no way can handle that. I get no way to handle this. No problem. And then I'm going to do it anyway, neglect this two. And then I'm going to admit the two error, and if it's this is this. And then I'm going to cut the line, maximize this marginal. Well, this idea sounds good. But you can neglect this two to get a good training, but that not means it's good to your test case. Again, because that just handle these 2 points. How about the test case have a bunch of points here, some here, right? And then your idea is not going to be perfect, at least not the best. Okay, this is how you get a question, a problem you need to formulate into math. Again, I have to find a trade-off. What's the trade-off? If I can minimize this, I can maximize the margin. And the bigger is the margin, and the more error I'm going to have. I would mean because you're going to cross the line by far, and the more error you're going to have. And if you narrow this, the error will be smaller, but you may still have. It really depends. So my solution is, I still want to minimize this total. This is the penalty for your misclassified example. Each of this number, see, minus this much, that's the error. Each of this is going to be a penalty associated with this constant c. We really don't know the c. Until we do the computation, find the one c, give me the minimum test error, then I take that c. And then I'm going to let this c be determined in the end, not in the beginning. And then, overall, I minimize this. Kind of like the minimum description principle. You remember this, there's two things for the penalty. One is the cost for you to build the tree, the length of the tree. But another one is the arrow, the penalty for your arrow, right? You remember the two pieces? The cost is the cost to build the tree and the cost of the arrow. Here is again the cost of this margin and the cost of this arrow. And then we're going to do that. And the same, similar constraint. Again, this is a quadratic property. Usually put a square here sometimes, depends. Sometimes put even a cube here, depends on what the application is. So now here this one has a k. K either equal 1 or 2 in most algorithms. K equal 1 or 2 is the penalty of the arrow. See what the errors are here. See this one, you get a penalty. See, and this one you get the penalty. Can you see it? So when you have this is equal 0 in this point, that's equal 1. This is equal negative 1. Did you see the margin? On the right hand, this line equal 0, and this line equal negative 1. This line equal positive 1. So this sigma is here and here, 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 here. You have to add those to the middle line. That's the penalty for your marginal. So we do that. Now, first, does this make sense to you? We got to now treat the thing with two problems. One, I need to maximize the margin, means minimize this penalty of this coefficient. And another one, I need to try to minimize this error. Now your trade-off is, if you make this narrow, and then you can get this out of the error. Can you see it? If I narrow down a little bit, I can get this two out, even this one out of the error. But my model will be overfit very much. You can get out of them. Does not mean your test case, your real case does not get too close. Are you with me? You're going to overfit your model. This narrow model was not good for the data really similar to this. You have to admit the error. On the other hand, if you make the margin too big, you're going to include more error. See, like those now is included. So how do you adjust this C? In the end, is how do you pick up this C at the perfect penalty? Just like you spank your kids. You cannot spank it too heavy. You cannot spank it too light. It's just that you need to spank it just right. They're going to learn the lesson, but you will not destroy the relationship. In the same way, you get this penalty, you need to be perfect. That's the computational part, the beauty of that method. And they're going to not determine in the beginning, but they're going to determine in the end. After you do the validation test and a little bit, that's called empirical. This is an empirical solution. And then you're going to figure what type of problem will put the data C is the best solution. And that's the idea. So when you use the Weka, you're not going to go from the Explorer. You need to go from the experiment. We're going to show you later on. But next hour, if we figure out everything, I'm going to show you how to do it in the Weka. And then I sent some R code there. And then if you use R, I think that will be easier. Okay, so how to penalize is by the C. So now what you're going to do in those details is, well, that's the same thing. You put the C by this, put the number here. Last year I went into a research talk. They're talking about this, the parameterless. How you're going to maximize doing those. Mathematicians, they can spend a couple of years to figure out one little bit of things. That's the natural thing. Oh, I lost the patient of that. But anyway, that's the algorithm. There are a lot of people do research. But if you really want to understand the Lagrange method, that's a powerful tool. You don't have to, because I have this toolbox in the MATLAB. They have the most powerful algorithm anyway to do this. because the optimization been in the world since Lagrange. That's a couple hundred years. And there's a lot of beautiful algorithm. It's built in the MATLAB, you can call. And you can use the toolbox. You can just fill in the blanks, the spreadsheet. And got parameters, they can run it for you. So if you have interest, you want to run, you just look at my module. But it's important how there's all different setting. A lot of research needed that. Because things always come back. This is a discrete type.